In this video, we will introduce the ICRA 2020 paper Contact-Based In-Hand Pose Estimation using Bayesian State Estimation and Particle Filtering. To start with some background, our goal is to assemble machines like the ones seen on the left with autonomous robots. These videos are taken from a human demonstration for the World Robot Summit Assembly Challenge, which represents a current benchmark for autonomous manufacturing. On the right, we see the current state of the art in the industry. Jigs and grippers that are specially produced for each part are used to position the grasped objects, so that the task can be separated into small independent problems. While this is very common, it is extremely costly and inflexible. Engineering is very often the largest cost and time factor in a robot automation system, and changing the work cell or production line to a new product can take weeks or even months. For more background, please feel free to read our journal article linked in this slide. Now, in the video on the right, we see that a lot of effort goes into the precise positioning of the grasped object. In general, the position of the object is not known precisely after it is grasped. Because of camera noise, the position of the robot, and many other factors, this is generally unavoidable. However, we want to know the position of the grasped object as precisely as we can, because even small offsets can cause a task to fail. The object may be dropped by the gripper, it might get stuck, or the robot may enter a protective stop. This is why we want a method that can determine the position of the object with very high precision without any specially manufactured jigs. Concretely, we set the following objectives. We want to be able to determine the pose of any object after it is grasped to sub-millimeter precision. We do not want to regrasp, and we want to minimize the amount of calibration that the end user needs to perform. We have found that reducing the complexity is very important for robot developers and operators, so we attempted to make the procedure as simple and generic as possible. Furthermore, we assume that the environment of the robot is known, and that the object model is known as well. We also assume that the object is rigid and does not change its position significantly once it is grasped. The main idea in our proposal is that we can use interactions with the environment to obtain information about the object's pose in the gripper. If we touch a surface with the object while we detect its contact, we limit the possible positions of the grasped object, and by repeating this process in different orientations, we can get a very good idea of where the object is. It should be easy to see the human intuition behind this approach, and one can also imagine that different actions can be used, such as looking with a camera. In this paper, we chose touching for its simplicity and ease of implementation. On the left part of the slide, you see that we start with a belief about the position of the object, which is a rough idea with some uncertainty. From this belief, we draw a number of particles. Each particle represents a possible position of the grasped object in the robot's wrist frame. When the robot senses that the object has touched a surface, we check the distance of each of the particles from the surface it is colliding with. We discard particles that are either too far away from the surface, since we detected that there is a contact, and we also discard those that penetrate too far into the surface. Only those particles which are just touching the surface remain as valid particles. We use those remaining valid particles to build a new belief about the position of the object, which is now more accurate. We know the position of the surface because we assume that it is known. But even if we were not sure about the position, we could easily obtain it by simply touching the surface with the robot. To summarize our approach, the object pose in the gripper frame is the state which we want to estimate. We represent this as the 6D pose of our object mesh plus an uncertainty in the form of a normal distribution. You can consider this the probability of the object being at any given pose. To reduce the uncertainty and to improve our belief about the system state, we propose to use touch actions. These actions allow us to gain information about the system state by using the knowledge that we already have about the environment and the fact that there is a collision. For the mathematical details, we refer you to our paper, but some explanation is useful to motivate why we chose this representation. In Bayesian terms, we can use the following description. The pose of the object xt is represented as a normal distribution around a 6-dimensional vector, which represents the probability of the object being at the estimated pose. The posterior probability, given a certain number of observations yt and ct, the collision state and the position of the robot wrist, gives us the estimate of the pose after taking the actions. This is given by the first equation. Because we do not have a way to connect this probability to the collision world directly, we use the particles to approximate the posterior probability, as shown in the second equation. We note that we could have chosen a pure particle filter solution, but this representation has advantages. First, it is compact and does not depend on the number of the particles that are used. Second, it is independent of the modality that is used and can be used efficiently with some of them, for example with vision. Third, it gives us a direct measure of uncertainty or potential information gain, which can then be used for reasoning and planning. For the experimental validation of our method, we grasp an object in 4 different poses and perform the 3 touch actions shown on the right. Then, we recorded the results and evaluated the performance of our method for different numbers of particles and initial settings. Each experiment was performed 4 times for a total of 16 runs. In the first table, the results for different initial errors and different numbers of particles are shown. We see that for sufficiently high numbers of particles, the error always decreases to under a millimeter. We were actually surprised to see that even for quite high initial errors of even 1 centimeter, the results were quite good. In the bottom figure, we see how each successive action improves the belief. The circles represent the covariance of the normal distribution, with each color showing a different iteration. The large circle is the initial state, and with each environment interaction, the estimated pose becomes more accurate. On the right, the same result is plotted using particles. We did not evaluate the calculation cost quantitatively, since it is overall very low. Modern collision checking is very fast and parallelizable, and the scene that we evaluate is not complex. Our code takes only a few seconds to run without any optimization, and should be easily optimizable to work in less than a second. Now, these results are good, but there are some things that we need to note. One is that the precision of the method fundamentally relies on the quality of the calibration of the collision surface. The position of the surface has to be known with very high precision for the method to work well. However, as we mentioned before, it is very easy to obtain it, even while the robot is running. You simply touch the surface with the robot and record the position, and no external measurement tools are needed for this. Second, the belief state representation as a 6D vector has limitations, mainly that rotations always happen around the object's origin, which may not always be what is desired. Solving this is part of the future work, and may be tackled either with a discontinuous distribution or by extending the belief state to allow a different center of rotation. Third, symmetry has an effect on the results. It should be obvious that we cannot obtain the rotation around the cylinder's axis, but more than that, if the rotation around the other axis is left unconstrained, particles can also end up flipped, which affects the result negatively. Last, touching a surface safely is quite slow in practice, and it takes at least 10 seconds. This is too long for industrial practice where cycle times need to be fast, so this is also part of our future work. In conclusion, we proposed a simple method for in-hand pose estimation, which allows us to estimate the object position after grasping to sub-millimeter precision. It works for any gripper and any rigid object, and it has very few requirements. You can use it with nothing but an object mesh and a way to detect collision, which any robot with force sensing can do. No calibration tools are required, and a single surface is enough to perform the method. No other modeling of the robot, or the gripper, or the environment is needed to use our method, and we would like to repeat that this simplicity is one of the strong points of our proposal. In future work, we want to make this method multimodal, so that we can use both touch actions and looking with a camera, for example. We hope to make our prototype available as a ROS package as well. Thank you for watching.